think you're going to like this chapter. Students usually like this chapter. I like this chapter. We're talking about polymers. All right, there we go. Chemistry 3111, you've made it. This is the last chapter we cover in organic chemistry too. And I know that for a lot of you, that you're thinking this is the end of the road for me in chemistry classes. That's great. I'm really happy to be here with you. And thanks for sticking it out for this entire semester. That's just fantastic. So we're going to end off with chapter 27. Just before we get started, I just want to remind you that we only cover sections 27.1 to 27.4. So those are the sections that we cover. The remainder is not covered, and the reason why is it's not covered on the ACS final. And I don't believe that any standardized exams like the MCAT or the DAT or the PCAT, I don't believe that those sections would be on those exams either. So let's get to it. And, before you begin this chapter, you probably noticed this when you read the chapter before coming to class today, that it might be a good idea to review some alkane chemistry and just, see where do the monomers come from. And then cationic polymerization of polystyrene, that was mentioned in section 8.4. I wouldn't really say it's 100% necessary for today, but as long as you have an idea of how a pi bond can behave as a nucleophile, or so anyhow, that would be good enough. And then the last part is radical polymerization. Well, that's the first kind of polymerization we're going to look at today. And of course, free radicals, are covered in chapter 10. So if you need to review your radical chemistry and your fishhook arrows, take a look over at that chapter 10. Now, if you have been reading the textbook very scrupulously for the entire semester, and for organic one as well, you might have noticed that polymers come up many times in the textbook before we get to this chapter. And the reason why we have to cover polymers before ending organic chemistry is because they are just ubiquitous in our everyday lives. It says here 50 trillion pounds of synthetic polymers are manufactured each year just in the US. I mean, the number of pounds, it's mind-boggling. But if you just look around you, I mean, I'm sitting at my desk right now at the university. I look at my Apple Pencil, that's made from polymers, as is my iPad, my desk, my iPhone case, my lanyard is made out of polymers. And I could keep going on, right? Even my clothing, some of my clothing is made out of polymers. And I'm talking just about synthetic polymers, right? And so, modern day society, we really do depend on polymers. And so again, I think we would be remiss to not talk about them a little bit before ending organic chemistry too. Now, if you want to go back in the textbook and look at some references to polymers that came up earlier on in the textbook, you can see that it did come up a few times. Far back as chapter 4, and there's a smattering of mention of polymers all the way up to chapter 25. So if you want to go back and take a look at that, I recommend taking the time to do that. But let's get started into some of the content in this chapter. And it says what we're going to deal with are synthetic polymers. Now, if you're wondering what's a non-synthetic polymer, well, that would be a biological polymer like DNA, RNA, polysaccharides, and proteins, enzymes, etc. So synthetic polymers, they're made by joining little units together, and we call those units monomers, and we put those monomers together and we make a polymer. And again, there's two categories, the synthetic and biopolymers. So we'll just put here biopolymers, just as a reminder, we'll put DNA, RNA, proteins, etc. Of course, polysaccharides fits in there. But what we're going to focus on in chapter 27 are synthetic polymers. And, what are some synthetic polymers that you would know already? Probably quite a few of them. I'm sure you've all heard of nylon before. Has anybody else heard of any other polymers? Does anybody know what bulletproof vests are made out of? I'm sure somebody does. Yeah, absolutely. So Kevlar would be a polymer. Yeah, absolutely. What about styrene, right? I'm sure you've all heard of styrene and polystyrene. And so polystyrene, which is partially what styrofoam is made from styrene. So maybe I should have put polystyrene or styrofoam, polystyrene. What about superglue? Has anybody here ever heard of superglue or using superglue on a cut before? Superglue is actually a polymer that's very common. A lot of people have that in the cupboard at home. So, we could keep on going on here with other polymers, but these are just a smattering of a few polymers that you would know in your everyday life. And we're going to cover a lot of examples here. So, something that could come up on the final exam would be this concept here. What happens is that when you make a polymer, you make it from a bunch of monomers. So you take these monomers, you see they all are derivatives of ethylene. So if you remember, ethylene is just this simple molecule here, CH2, CH2. This is called ethylene. So we have an ethylene molecule with some kind of R group on it, and you just keep adding a bunch of those monomers together, those ethylene derivatives, and then you end up making a polymer. So you can see that drawing the polymer is not overly difficult. All you have to do is connect the monomers together like this, right? And then you just get rid of the double bond, or the pi bond, if you will, and there you go. You've drawn yourself a polymer from a series of monomers. And we're going to get some practice on that today. I'll erase that to avoid confusion. But you can see that when you look at the polymer, you might be thinking, well, I could draw that, 100 units long. How long do I have to draw it? Well, the best thing that you could do is just identify what we call the repeating unit, the part that keeps repeating over and over and over. And then you redraw that repeating unit only one time, and you put it in a set of square brackets like is shown here. And then you put a subscript n and say, well, this just keeps repeating over and over. So we have the monomer, polymer, and then we have the repeating unit, which is just a representation of the polymer itself. So again, the square brackets, this is a shorthand, but I highly recommend using this. And we're going to use this many times just to put the repeating unit in brackets. So it says here, connecting only the atoms in the bracket over and over should accurately give the synthetic polymer structure. So all it's saying is, if you take the repeating unit that's inside these square brackets, you keep drawing it as a million times, it should make the polymer. And you can clearly see that here it would make the polymer, so that's a good thing. All right, let's talk a little bit about nomenclature. And IUPAC has a couple of ways of naming polymers. One, there's sort of a real systematic way of doing it, which can be quite complex, and so that is not covered in our textbook whatsoever. It's something I've only ever been introduced to maybe once in my life, because most chemists like to use a system of naming which is accepted by IUPAC, but it's more of a common way of doing it. And it's all we do is we take the name of the monomer. So pay close attention. All we do is we take the monomer. So say you have propylene, and if you're thinking, well, Mr. Dion, isn't that propene, right? So propene, right? You have 3 carbons and a double bond. Yes, you could call it propene, but the common name is propylene. And so to name the polymer, all you do is you put poly in front of the name. So polypropylene. For example, here we have styrene. So if you make the polymer of styrene, you call it polystyrene. And then, of course, there are many trade names of polymers that you're aware of. We already talked about nylon, and Kevlar came up. Teflon, there's another one. Teflon is, of course, used in non-stick cookware, and so I'm sure that most people are familiar with that. So let's take a look at some names of synthetic polymers, and you're going to see even more polymers that you recognize from your everyday life. Let's start at the top here. It says if we have the simplest possible, really, ethylene polymer that we can have, it would just be a polymer of ethylene itself, and that would be polyethylene. And if you're wondering, well, where would I find polyethylene in my everyday life? It's found in things like bottles, like bottled water or soda bottles, things like that. And of course, trash bags. It's a very inexpensive plastic or polymer. The next one is polypropylene, right? So this is propylene here. So maybe I could just write this in here. This is propylene. So polypropylene is the polymer. And of course, if I went back here, I could have written in here, this is ethylene. So you have polyethylene. Anyhow, polypropylene is found in carpets, and it says also car tires. I was actually unaware of that until I read this textbook. So there you go. Polypropylene is found in car tires. I guess I should write the whole name of correctly here. So oh no, I did have it right. Polypropylene. There we go. Anyhow, the next one is isobutylene. So I'm sure you've seen this molecule in your travels many times in Organic Chemistry 1 and Organic Chemistry 2. So polyisobutylene is used in caulking, in bicycle inner tubes, and some other things here. Okay, let's move on from there. So styrene, we already covered this one a little bit, but this is a styrene molecule. And it's usually at this point that my students start asking me, do I have to have all of these molecules memorized? The answer is no. I think that by now you should know what ethylene is. I would say you'd be in trouble if you don't know what ethylene is by now, or propylene, and then isobutylene. I think you should know that. Styrene is probably new in this chapter. Should you know it? I don't think it's a bad idea. Same thing with vinyl chloride. So this is vinyl chloride, but I don't demand that my students know vinyl chloride. So if we make polystyrene, again, that's used in foam insulation. An interesting thing about polystyrene, which you've probably heard of as styrofoam, is that the styrofoam that you and I are used to nowadays is not polystyrene. It's a polystyrene derivative that is doped with some other compounds to stabilize it, because the initial styrofoam was just this. It was just polystyrene, but it had a very poor stability and it would break down quite rapidly. So anyhow, so polystyrene is actually, it's got polystyrene in it, but it also has some other compounds in there as well to stabilize it. The next one is vinyl chloride. From that, you make polyvinyl chloride, which is, you probably recognize that, it's PVC, which is, of course, used in water pipes. The next one, so this one's got a long name. So let me show you a couple things here. This molecule is called alpha methyl cyanoacrylate. So if you have this compound here, this compound would be called acrylic acid, is the common name. So if you converted it from a carboxylic acid into a methyl ester, then you'd call it methyl acrylate. And then, of course, this is the alpha carbon right here. So if you put a cyano group on it, right, you call it methyl alpha cyano acrylate. So hopefully that name makes sense to you now. But polymethyl alpha cyanoacrylate, that polymer is actually superglue. So, if you're wondering, well, why is this stuff so reactive? If I put vinyl chloride on my hands, is it going to immediately polymerize into PVC? No, but we know that if you put superglue on your fingers or anywhere, it's going to start to polymerize immediately and turn into that glue, or harden, if you will. And so there's a good reason for that. And I was just looking at my notes here quickly. I have the structures of crazy glue and all kinds of other things. So I don't know if anybody here has even heard of crazy glue, but it was popular when I was a kid in Canada. And crazy glue, the only difference between crazy glue and super glue is literally this. They just changed the methyl group to an ethyl group. That's it. And again, this might not be of interest to you, but it even starts with a K. Crazy glue. They used to run commercials for it all the time when I was a child. No, Elmer's glue is not the same thing, though. That's a much weaker kind of glue. This is like a glue that would stick to your fingers, and rip your skin off, stuff like that. Not the kind of glue that they would give to children. Anyhow, has anybody here ever heard of Dermabond before? Dermabond. It's like a super glue that's put on wounds sometimes, right, Tiana? So if somebody cuts themselves. So if you're wondering, well, what's the difference between super glue and Dermabond? Because sometimes you'll hear of people putting super glue on a cut. Dermabond, oh jeepers, I don't have enough room to write it here, but just in case anybody is interested at all, I don't think this is on the exam, but Dermabond looks like this. The only difference is that you have an octyl group. So 1, 2, 3, 4, 5, 6, 7, 8. You have this big 2 octyl group out here. Anyhow, and if you're wondering, well, why would they make something like this, Dermabond? Well, you can imagine that the reason why they don't put super glue on a person in the hospital and crazy glue is because there's some kind of skin irritation with these compounds, and with Dermabond that is alleviated. So when they put super glue on you in a hospital, they're not actually putting super glue on you. They would be putting something like Dermabond. Well, that's Mary. I just read your comment. I don't know if I'm scared, because there's nothing really toxic in it that I could think of that could hurt you. And it has, it's gotten me out of a jam once or twice. But Mary, if you don't feel comfortable, right, you don't do it, right? You just get a Band-Aid or something like that, or head to the nearest hospital, right? Anyhow, has anybody ever used super glue on a cut? I did. I was with a friend of mine a couple of years ago, and I cut myself quite badly in the woods, and that's all we had. Anyhow, all right, I digress. Let's move on from there. But anyhow, it is kind of an interesting thing, the whole Dermabond and super glue thing. Kind of a fun conversation. And the next one is polytetrafluoroethylene. And so you have tetrafluoroethylene. Now, that is used for Teflon. Has anybody here ever used Teflon before, like a nonstick pan? I'm going to assume yes, that somebody in the class has. You want to go, so Amelia has. Anyhow, do you want to go right back to basics of Organic Chemistry 1 and intermolecular forces? Right, if you think about the second period of the periodic table, you go from lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. What happens as we go from left to right across the period? Do the atoms get larger or smaller as we go from lithium to beryllium to boron to carbon to nitrogen to oxygen to fluorine, right, to neon? What happens as you go from left to right across the period? Do the atoms get larger or smaller? Can anybody answer that? Larger or smaller? So as you go in this direction, okay, so here's some review for you. Okay, as you go in this direction, they get smaller. Okay, it's counterintuitive, isn't it, right? Because you think, well, more protons, more neutrons, right? This is back to Gen Chem 1, all right? These are the atomic trends that you have to know. The elements get smaller, and the reason why it's based off of effective nuclear charge, right? Or Z effective, right? So the elements actually get smaller and smaller because the nucleus is adding more protons, which are positively charged, but all the valence electrons that are being added to a shell in the same principal quantum number, either 2s or 2p. And so what happens is that means that fluorine is actually a very small atom and is non-polarizable. Okay, so small and non-polarizable. And if you remember, polarizability is the ability to distort an electron cloud. And so since the fluorine is so small and non-polarizable, it has extremely weak London forces with anything, okay? Very weak forces. And so that is why food doesn't stick to Teflon cookware, because it's all covered in fluorine on the surface. And again, fluorine is a very small atom, non-polarizable, and it won't interact with the food and be attracted to it in any way. Hopefully you learned something on that one. Let's just practice one more time. What about, what's the trend if we go down a group, though? If we go down a group, do the elements get bigger or smaller as we go down a group? Yeah, larger for sure, exactly. So we'll go here, larger. Anyhow, but you have to, if you're interested in taking MCAT or something like that, I would certainly review the concept of effective nuclear charge. Okay, that's a huge concept in Gen Chem 1. Anyhow, that was a little interesting rabbit trail on Teflon there for a second. Anyhow, so this one just says draw and name the polymer that results when each of the following monomers undergoes a polymerization. And again, this is probably another point where my students will interrupt me and say, Mr. Dion, do I really have to know that the name of this molecule is vinyl acetate? And I would say no. I would give you the name. So this one is vinyl acetate, and this compound is called alpha butylene. Butylene, like that. So if we want to name the polymer of vinyl acetate, it's going to be polyvinyl acetate. But the thing is that when we have two words, so two words, the way that we do it is we put poly first, and then we put vinyl acetate, the two words in brackets, acetate. So now let me show you how to draw a polymer. If this is the monomer, the way that we're going to draw the polymer is this. All we have to do is eliminate the pi bond, right? And then we're just going to make sigma bonds between this carbon and so on and so forth, right? And just repeat that over and over. So look, we're going to put CH2, okay? And now the molecular geometry is changing from a trigonal planar to tetrahedral. So then we're going to have OAC, so that's our acetyl group here. And then we just repeat the same thing over and over and over. And if you want to do it 10 times, knock yourself out. That's weird. Kidding. But seriously, you can draw it as many times as you want. I'll just do it 3 times here, like that. Okay, and then we're going to put a square bracket around the whole thing and put N down here, and that's it. That's the structure of your polymer. Now, if you just wrote something way simpler, if you just said, well, Mr. Dion, all it is this. I'll just draw, let me move this up here. I'll move it over here. So if you did this, if you just said, well, come on, it's CH2, CH, OAC, and then you connected it like this, and you put N down here. That's perfect. There's nothing wrong with that. That is 100% correct. It's just a much simpler way of doing it. Now, keep in mind that alpha and alpha butylene, alpha is not a word, it's just a prefix. And so the name is going to be polyalpha butylene. So we'll just write here polyalpha butylene, like that. And so to write the polymer, we're going to put CH2 again. We're going to methylene, and then we have CH. Then we have an ethyl group up here, so CH2, CH3. And then we just keep repeating that. So CH2, CH, CH2, CH3, so on and so forth, like that. There you go. And if you just did it once, if you tried to make it even simpler, and you just said, look, the repeating unit is this, CH2, CH, CH2, CH3, like this, and you said that, Mr. Dion, is the repeating unit. That's the exact same thing. There's nothing wrong with that at all. Give me a thumbs up if you follow me on naming a polymer and drawing a polymer from a monomer. Awesome, awesome. If you're sitting there thinking, is that it? Is that all there really is to it? That's pretty much it, my friends. There isn't much to it other than that. All right. So let's see here. Okay, let's move on from there. It says nomenclature of synthetic polymers. So sodium polyacrylate, this is a funny one, is a synthetic polymer used in diapers. Because of its ability to absorb several hundred times its own mass in water, this extraordinary polymer is made from another polymer, polymethyl acrylate, via hydrolysis of ester groups. So draw and name the monomer used to make polymethyl acrylate. So if it's polymethyl acrylate, then that means that methyl acrylate must be the monomer. So we'll write down here methyl acryl. What's up with my handwriting today? Acrylate, like that, okay? And then our monomer is going to look something like this. So now we're going to take these two carbons and we're going to connect them with a double bond. And then we're going to put our two hydrogens over here. And then we have another hydrogen here. And then we have the methyl ester over here. And there you go. Methyl acrylate. That is it. Everybody with me on that one? Or any questions about that one? All right, great. Awesome, awesome. Well, let's keep going. And before we take our first break, I wanted to talk about copolymers with you for a couple of seconds here. So let's take a look at copolymers. And there's a few types of copolymers that we need to cover, and you just need to know their definitions more than anything. So all the polymers that we've been discussing so far in sections, or I guess the focus of section 21.1 and 21.2 was homopolymer. So that was just a polymer made out of one ethylene subunit, and then they build off that. So it's all the same type of monomer. Well, if you mix two different monomers together, you get what's called a copolymer. And one that everybody is familiar with is saran. Okay, I know you've all heard of saran wrap. Well, saran is a trade name of a polymer. It's a polymer of vinyl chloride and vinylidene chloride. And what's interesting is if you make a polymer of vinyl chloride and a polymer of vinylidene chloride, they have their own properties, each one of them. And then if you mix them to make saran, which again is a polymer of vinyl chloride and vinylidene chloride, you end up with something with new properties. So that's one of the great things about chemistry is you can mix and match, and you end up with brand new characteristics. And so that's why material science is such a cool area of research in chemistry. But anyhow, so when you mix vinyl chloride and vinylidene chloride, you get saran. So you can imagine that if you had to draw a copolymer, you just alternate, right? Let's say you call this one, you call this part A and you call this part B. Well, then you just repeat with another A, and then it goes to a B, et cetera, et cetera. So again, and I can't stress this enough, and this is something that you should know by now, is that if you were to make, an isomer of another compound or compounds, you end up with something that has new properties. So new polymers are being discovered all the time. So here are some copolymers that you would know. Of course, saran, we just covered that one. SAN, I don't know if you would know it by its name. So SAN stands for styrene and acrylonitrile. the one in the middle here. But I know you all know about things like Tupperware, which is dishwasher safe, right? Or any kind of dishwasher safe plastics. I'm sure you see those every day. Even, you know, yogurt containers, you can put them in the dishwasher and they're fine. So styrene and acrylonitrile, we call that a SAN. The next one is ABS, not the type of brakes. This stands for acrylonitrile, 1,3-butadiene, and styrene, and they have them here in some kind of funky order though. But so you mix these three polymers and you get ABS plastic, which is used in helmets. Is one place that I know it's used. I wasn't sure about car bumpers, but if whatever they say, luggage, I guess if you buy good quality luggage, it might be made out of ABS plastics. The next one is butyl rubber, which is made from isobutylene and isoprene. And again, you don't have to memorize any of these. It's more just kind of food for thought of making the copolymer. And the butyl rubber is used in things like, you know, inner tubes and, of course, you know, sporting goods like, you know, basketballs would be an example, and soccer balls, maybe stuff like that. Footballs, I suppose. Hexafluoropropylene and vinylidene fluoride, those go together to make something called Viton. And I'll be honest, I didn't even know what Viton was until I, you know, started working as a chemist. And the reason I know what it is now is because Viton is used to make very chemical resistant gaskets that we would put in on reaction flasks sometimes to prevent corrosion. So let's say you're doing a reaction in acid at a super high temperature, that can just chew apart plastics like anything or any kind of rubber. And so Viton is a very resistant rubber or polymer. And it says gasket seals, and then of course fuel lines would be another example of where it could be used. So what are the types of copolymers that we can have? Well, so far I just kind of talked about putting the polymers together, but there's different types of copolymers. The first two are random and alternating, and I'm sure you can figure that out on your own what that means. Excuse me. So random just means that, you know, there's no organization to it. The polymers are mixed together, but they're mixed together in a random order. Whereas alternating means they're going to alternate A, B, A, B, A, B, or A, B, C, A, B, C, A, B, C. But the thing about an alternating copolymer is that even if it's alternating, it's still going to have random sections in it. So that's why I put a star by here. It's just to remind you that even the best alternating copolymer, it's very difficult to control how the polymers are going to go together. And so you can still get some random copolymers in there. Also, you can have what we call block copolymers. And well, a block copolymer is kind of where you put two homopolymers together, like these subunits of them, I guess. So you have like a subunit of one homopolymer and then a subunit of the other. You stick them together, you get a block copolymer. Or if you have a long chain of one type of polymer and then you just attach another homopolymer to it, we call that a graft copolymer. So you should just know the idea of the definitions of these four types of copolymers. So random, alternating, block, and graft. That would be kind of what you would want to know here. All right, so if you're wondering, you know, well, what kind of questions would you ask me about copolymers? Let me show you, okay? Let's take a look at a couple of examples here. The first one says, draw a region of an alternating copolymer constructed from styrene. So we already looked at styrene. Maybe I could color code this. So here's styrene and ethylene, like this. So let's just draw an alternating copolymer. So remember, alternating copolymer goes like A, B, et cetera, et cetera. So why don't we do it like this? We'll start with the styrene. We'll color code it here. So we've got CH2 and then a methine. And then we're going to attach that to ethylene. So CH2, CH2. Then we're going to attach that to another styrene. So CH2 methine with a phenyl. Then we're going to attach another styrene like this. We'll do two more. Okay, so then we've got a styrene, this, and then we've got a ethylene like that. And then if you put the whole thing in square brackets, comme ça, as we say in French, there you go. That would be an alternating copolymer. Does that make sense to everybody? Styrene, ethylene, styrene, ethylene. Give me a thumbs up if you're with me on this. Okay. And in the textbook, I'm not sure how he does it. I don't look at the solutions manual a whole heck of a lot, but he might choose to draw every single bond, you know, explicitly like that. If he does, I say good for him, you know, good for David Klein, but That seems like a lot of unnecessary bond drawing, at this level of the game. You're wrapping up the course. You should know how to draw a condensed structure by now. But if you want to do that, that's totally fine. All right. So let's take a look at the next one. This also deals with copolymers. It says draw a region of a block copolymer constructed from propylene. So propylene is this compound, and then vinyl chloride. And vinyl chloride is this compound. So if it's a block copolymer, why don't we just put 3 and 3? So we'll do something like this. We'll do A, and then we'll do B, B, B. That will be our copolymer. And of course, if you've already done this at home and you're like, well, I put 5 in a row and then another 5, that's fine too. I take no exception to that whatsoever. So let's pencil this in here. We'll start with the propylene. So we're going to have a methylene and then a methine with a methyl. And that's attached to our vinyl chloride. So, oops. It's a block copolymer. Didn't I say I was going to put 3? I did. Oh, Mr. Dion. What are you doing? There we go. That looks a lot better. Like that. And then we've got our vinyl chloride. We'll make 3 of these. Do another one. This. And then that'll be enough. Something like that. So yeah, there's our block copolymer. Everybody with me on that one? And again, it's not meant to be a mind-boggling exercise. It's just kind of, do you understand the concept of it? Okay, I think there's one more question about copolymers. So let's take a look at it. It says, identify the monomers required to make the following copolymer. It's alternating. And you can clearly see that one of them comes from here. And then the other one comes from here. Can anybody name one of them? Just either one of the monomers that this comes from? And it's not a trick question. I just want to see if you picked up on any common names. And if you can't name it, it's fine. Anybody recognize either of these monomers? What they? Yeah, thanks, Maria. Maria got one. Yeah, absolutely. This one would have come from this. Yep. And this is styrene. Styrene. Does anybody recognize the one in red? So that would come from this. So CH2, this guy here. So this is isobutylene. Isobutyl. There you go. So isobutylene and styrene are the monomers that are used to make this copolymer. All right, there you go. And again, you don't have to memorize all of these compounds. I don't think it's a bad idea at this point for you to know the name of isobutylene and styrene. These molecules could come up in biochem, so not a bad idea to know those monomers. Well, the next part of the chapter says polymer classification by reaction type. So there's a bunch of different ways that we can classify polymers. In section 24.4, it covers, how we use a different type of reaction, whether it be radical polymerization process, cationic or anionic, to distinguish the different types of polymers. And we are going to cover that section next. So we're going to look at radical polymerization, then cationic, then anionic. But then after that, it gets into some other ways to classify monomers. For example, mode of assembly is covered in 27.5. Did I put 24.4 when I meant to put 27.4? There you go, Mr. Dion. 27.5 is covering them based on their structure. So 27.6, my mistake. And then properties is covered in 27.7. There, that makes a lot more sense. So we're going to skip those last 3 sections, okay? I'm going to put here skip. And when it comes to type of reaction, there's 3 types. There's radical, there's cationic, and there's anionic. And what we're going to do right now is we're going to take a short break, and when we come back, we're going to get into all of these 3 types of polymerization reactions, meaning free radical, cationic, and anionic addition to make a radical. And that will be the last section that we cover in organic chemistry 2.